Video assignment 14, sketching graphs of functions, part 1. We're going to start off with example 1. We're going to analyze and sketch the graph of f of x equals 2x squared minus 8 over x squared minus 9. Let's start off with the domain. Well, the only problems with the domain are where the bottom is equal to 0. So that's the set of all x such that x does not equal plus or minus 3. And then let's go ahead and find our x-intercepts. How do we find x-intercepts? We set the y value equal to 0. So we're going to set that y value equal to 0. If you multiply both sides by the denominator, you just have this. Solving this, I could factor out a 2. I would get x squared minus 4. 0 equals 2 times x plus 2, x minus 2. So we've got x equals plus or minus 2. So our x-intercepts are going to be at -2, 0, and 2, 0. From there, we need a y-intercept. If you remember, to find the y-intercept, it's just a matter of finding f of 0, which I think gives us -8 over -9. In other words, 0, 8/9. Let's talk about symmetry. That's a matter of noticing whether you have an even or odd function, right? In other words, what's happening with f of -x? This is for symmetry. This was for y-intercept. This is for x-intercepts, okay? If we put in -x for all of these, you'll notice all the x's are being squared, right? And so we end up, when you square negative, it's just positive. So we get 2x squared minus 8 over x squared minus 9. That's the original function, f of x. And when that happens, that means, therefore, f is an even function. And if f is an even function, that means it's symmetric about the y-axis. All right, can we find horizontal asymptote? The way we find horizontal asymptotes is we take the limit as x gets huge, right? Horizontal asymptote is what we call, it has to do with end behavior, and we want to know if the function is eventually approaching a certain number. And so we take the limit as, so this is for horizontal asymptote here, we take the limit as x approaches infinity or negative infinity of 2x squared minus 8 over x squared minus 9. And if you remember, the way we talked about doing this back in our chapter on limits is we multiply top and bottom by 1 over x squared to get something that looks like this. And for huge x, those two fractions are going to go to 0, and we're left with 2. So we have a horizontal asymptote at y equals 2. Vertical asymptotes are where the denominator equals 0. That's going to happen where x equals -3 and x equals 3. So we've just done a whole bunch of work to find all this pre-calc information about our graph. And we could do a little more even. We could plot a couple points. We could just pick x values and see what they give us, but we're not going to do that. We're going to now switch over and do some calculus, meaning we're going to figure out where this function is increasing and where it is decreasing. So let's go ahead and find a first derivative. So here we go. F prime of x, you're going to have to use the quotient rule, the bottom, times the derivative of the top, which is 4x, minus the top, times the derivative of the bottom, which is 2x, all over the bottom squared. And so that's going to give us 4x to the third minus 36x. Distributing a negative and a 2x, we're going to get minus 4x to the third plus 16x all over x squared minus 9, like that. And that's going to simplify to just give us negative 20x over x squared minus 9 quantity squared. Okay. So that means we have critical numbers. Okay. Definition of critical numbers, they have to be domain values. 3, -3 are not domain values. So there's only one critical number at x equals 0, guys. Now let's go ahead and find our second derivative. And if you're thinking, this is a lot of work for one problem, you're thinking right, it is. So I'm going to take my first derivative and use the quotient rule again. So I'm going to have the bottom times the derivative of the top minus the top times the derivative of the bottom using chain rule all over the bottom squared. Let's go ahead and simplify it down. I'm going to factor out an x squared minus 9 to the first power. And I'm going to get x squared minus 9 times negative 20. Here I'm going to get a positive, I guess I could have factored out a 20 also, huh? Oh well, I didn't do that. Here I'm going to get 2 times 2 is 4 times 20 is going to give me 80 x squared, like that, all over x squared minus 9 to the 4th power. I can cancel my x squared minus 9 on top and bottom, so I just have an x squared minus 9 to the 3rd power now. If I distribute my negative 20 x squared, my negative 20 to the x squared, and add it to this 80, I'm going to get 60 x squared, and then I'm going to get plus 180 when I multiply there. If I factor out my 20, which I should have done hours ago, I get a 3x squared plus 9 over x squared minus 9 to the 3rd. So now I'm going to find my possible points of inflection, P-boy. Anyway, possible points of inflection, where, again, possible points of inflection are places where the second derivative either exists, or well, let me back up. Domain values, remember what Toma mentioned, domain values where the second derivative either equals 0 or fails to exist, okay? Can you ever make the numerator here in yellow 0?
Nope.
No. You're taking a number and squaring it and adding to it. It will always be positive, okay? No matter what you plug in, unless you plug in imaginary numbers, but we're not doing that. So, and positive 3, negative 3 are not in the domain. So guess what? We have none. There are no possible points of inflection. All right. So we have laid the groundwork to graph this thing, okay? We have a vertical asymptote at -3. I always like putting my asymptotes in first and then work around my asymptotes. It gives me a framework around which to graph. And then we have a horizontal asymptote at y equals 2, like that. What we need to do is we're going to build one big table. And what we really need is we need to see where things switch from increasing, decreasing, or concave up, concave down. And so that happens at critical points and possible points, or at points of inflection, but it also happens at asymptotes. So when we build our table, we want to include asymptotes, critical numbers, and possible points of inflection, where we're going to put our intervals vertically, including, again, our possible points of inflection, our critical numbers, and our asymptotes. So we're going to go from negative infinity less than x less than -3. Then we're going to see what's happening at -3. Then we're going to go from -3 less than x less than 0. And then we're going to see what's happening at 0. Then we're going to go from 0 less than x less than 3 and see what's happening at 3. And finally, we're going to go 3 less than x less than infinity. And so our table is going to include those intervals there. Okay, so this is our interval. And so we're going to look at f of x for some of these, f prime of x for some of them, f double prime of x for some of them, and then we're going to write up a conclusion. Once we have this table set up, we'll be ready to finally graph this thing. The way we're going to fill in this table is very similar to the other tables we've done. We're going to take a value in the interval and we're going to plug it into f prime and f double prime. So let's go ahead just to maybe get this a little more organized. Off to the side here, and there's some nice things here that are going to make us let us work a little less hard. You're going to notice that the bottom here is always positive, and I'm saying everywhere where it's defined, of course, but always positive. We don't have to worry about plus or minus 3 because we already know what's happening there. And then over here, the top is always positive. Okay, so then we only need to really think about what's happening in the numerator. So if we look at f prime and we pick a value between negative infinity and -3, like throw in a -4 up there, we're going to get positive over positive. So we have a positive here. If we plug in -4 down here, right, we're going to get 16 minus 9, which is positive. So that gives us a positive over positive. So we get a plus sign there. At x equals -3, everybody's undefined. Everybody's undefined. And we know that we have a vertical asymptote there. From there, if we plug in a value between -3 and 0, like -1, over here, plugging in -1, right, we're going to get f prime being positive. But if I plug in -1 down here, I'm going to get 1 minus 9, which is -8 to the third, which is also negative. Okay, so in that case, we get a negative and positive divided by negative, which is negative. At x equals 0, we saw from above that that's our y-intercept, 8/9. F prime at 0, if I plug in 0 over here, I'm going to get 0 in the numerator and positive in the denominator, so that will be 0. And then if I plug in 0 over here, I'm going to have, again, a positive divided by a negative, which is negative. Okay, and as you go through this, you want to be kind of careful because you make one little mistake and your whole graph's going to get jacked up. Let's plug in a +1 here, giving us a negative over a positive right there. Let's plug in a +1 here, giving us a positive over a negative, which will be a negative there. At 3, again, we are undefined everywhere because we have vertical asymptote. And finally, we're going to plug in, let's say 4. If we plugged in 4 in the numerator, we'd have negative over positive, giving us a negative here. And if we plugged in 4 over here, we would have a positive over positive, which is positive. Okay, hope I didn't do that too quickly, but you can imagine what I've done. All I did was I plugged in values, see if we're positive or negative. Now, from this, we get a bunch of conclusions. Anywhere f prime is positive, we are increasing. And anywhere it's negative, we are decreasing. That's for f prime. Anywhere f double prime is positive, we are concave up. Anywhere it's negative, we're concave down. Okay, so we know everything we need to know about increasing, decreasing, and concavity. Now, look right here, please. I want to say something about what's happening at 0.8. Notice that we have a function that's increasing on one side, increasing here, and then decreasing on the other side. So that, and we have a horizontal tangent line in the middle. So what does that mean using the first derivative test? We have what there?
A local max?
Exactly, a local maximum. That's exactly right. Okay. Another way of seeing that using the second derivative test is we have a horizontal tangent line and we're concave down. Remember, we looked at pictures of that, right? If you're concave down at a point and you have a horizontal tangent line, you have a local max. So that's another way of thinking about it. All right, so now, believe it or not, we're ready to start graphing. We had an x-intercept and a y-intercept way up there. Two x-intercepts, one at -2 and one at +2, and a y-intercept at 8/9. So I've got an x-intercept here, an x-intercept here, and a y-intercept right there. If we look at this first region here, between -∞ and -3, we are increasing and concave up. Well, because we have this horizontal asymptote, it has to look like this or like this. But if it's increasing and concave up, we kind of don't have a choice. It kind of has to do something like that. Okay? Notice we're increasing and we are concave up. Then we have our vertical asymptote. And then we're being told right here that it's increasing and concave down. Well, that's going to look something like increasing and concave down. We get to our local max, and then we're decreasing and concave down. That's just going to do this. And then finally, we have another vertical asymptote, and here we are decreasing and concave up. So again, it's either going to do this or it's going to do this because of our horizontal asymptote. But if we're decreasing and concave up, that's going to have to be the one on top. In other words, doing something like that. And believe it or not, that's what our graph looks like. Quite a bit of work to get there, but we've done it. And it does get a little bit faster the more you do it, of course, like all this stuff. But there it is. That is the graph of our function.
For the values, the x equals -3, x equals 0, x equals 3, are those just coming from the domain? How it,
are you talking about the intervals
on the intervals?
that I'm using?
Yeah.
Yeah, so Karash is asking a really good question. He's saying, where is all this garbage coming from? And so what you're going to use, let's write it down so we remember this because we're going to need it. We use critical numbers, possible points of inflection, and vertical asymptotes. And the reason, and you can see it in the graph, we can get a change in increasing, decreasing where we have a vertical asymptote, right? And yeah. So we have to check on either side. We can also have a change in concavity at a vertical asymptote, so we have to check on either side. And so that's kind of the reasoning there behind it. Does that kind of make sense?
Yeah.
Okay, cool. So real fast, I think we actually did a pretty good job graphing this thing, but just for kicks, if we look at GeoGebra real quick, just to make us feel good about ourselves and all that hard work we did, there's the graph in green. That's pretty good. We did all right. Any questions?
So for these problems, we're just using what we learned in pre-calc for the first half, and then what we did in last class with the table to make the graph, and that's basically it.
That's basically it.
Okay.
Okay, let's go ahead and see what trouble we can get into with this next one. So let's go through the same ideas. I'm going to go through the early ones kind of fast because, again, this is a lot of pre-calc stuff. So we're going to do domain first. Is going to be the set of all x's such that x does not equal 3. We're going to have our x-intercepts. To get x-intercepts, that's where we set y equal to 0. In other words, what's going to make the numerator 0? Okay, so for x-intercepts, we have 0 equals x squared minus 8 over x minus 3. The way you make a fraction equal to 0 is just making the top equal to 0. So x is equal to the square root of 8, which is 2 root 2, actually plus or minus. Okay, so that's going to be plus or minus 2 root 2 comma 0. Or if you put it into a calculator, you're going to get plus or minus 2.83 comma 0. The y-intercept is what we get when we let x equal 0. That's 0 comma 8 thirds. Or if you want a decimal, that's 2.67. Symmetry, there is none here. That's because if we plug in a negative x into the function, you can see what we get here, and it is not symmetric about the y-axis because it doesn't equal the original function, and it's not equal to the negative of the original function, so it's not symmetric about the origin either. This is the same as checking whether the function is even or odd. For the horizontal asymptote, that's where we take the limit as x approaches infinity of x squared minus 8 over x minus 3. And the way we did this in our class, again, if you remember the shortcut from pre-calc, fine, but we multiply everything by 1 over x, and we get something like this. And these guys are going to zero out right here and here. But as x goes to infinity, this whole thing is going to go to infinity. So there is no horizontal asymptote. And if you recall from pre-calc, there might be a slant asymptote or an oblique asymptote, right? So let's remember how to do a slant asymptote or oblique, same thing. This is where we do our long division, x minus 3 into x squared minus 8. And I think that's going to go in x. We get x squared minus 3x. When we subtract, we're going to get a 3x minus 8. And then we're going to have a plus 3 here, which will give us 3x minus 9, which will give us a 1. So we get plus 1 over x minus 3. Okay, that is another way to write our function. Okay, and if we consider huge x's, this part here goes to 0. So we have a slant asymptote at the remaining equation, right? If you want, I can discuss that in more detail. I kind of assume that it was discussed in pre-calc in considerable detail. So does anybody want me to talk a little bit more about the slant or oblique asymptote? Okay, if you want, once we graph it, we can have that discussion in more detail because then I'll have a graph to point at and I can kind of show you how it works and I'll be happy to have that discussion. But for now, that is our pre-calc stuff. Let's go ahead and find f prime of x so we can get critical numbers. f prime of x is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. This simplifies, I'm going to go ahead and just do it. 2x squared minus an x squared gives me an x squared, negative 6, and then plus 8 all over x minus 3 squared. And I think that numerator actually factors x minus 2, x minus 4 over x minus 3 squared. Nothing cancels, unfortunately. Let's find f double prime. While we're at it, get all our derivatives out of the way. I'm going to use this one here and do the quotient rule again. So we're going to do the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. I'm going to factor out an x minus 3 so I can cancel it in the bottom. So we're going to have x minus 3 times 2x minus 6. And here we'll have minus x squared minus 6x plus 8 times 2. And that x minus 3 in back came out. So we've got an x minus 3 here. Whoops, I forgot to do something in the denominator, guys. That's to the 4th power down there, right? You square the denominator. All right. So now multiplying, I'm going to have 2x squared minus 6x. Wait, 2x squared minus 6x plus 18 minus 2x squared plus 12x minus 16. I'm distributing all the way out here. I'm going to cancel to get x minus 3 to the 3rd. The 2x squareds cancel. The negative 6x's and the 12x cancel. We're just going to have 2 over x minus 3 cubed. That turned out nicely. So we have critical numbers at any domain value where the derivative equals 0 or fails to exist. So that's going to happen at 2, right? I'm looking over here. 2 will give us a derivative of 0. 4 will give us a derivative of 0. And 3 is not part of the domain, as Toma just pointed out in the chat. And then possible points of inflection, p-poi. For that, looking over here, you can't make f double prime 0. So guess what? None, because 3 is not in the domain. All right, we're ready to start thinking about a table. Okay, so just as Karash asked at the end of that last problem, how do we come up with our intervals? We use critical numbers, possible points of inflection, and vertical asymptotes. So we have our critical numbers 2 and 4 and our vertical asymptote at 3. And that's it. So we're going to build a table and we're going to have an interval. Okay, so our intervals are going to be what? Negative infinity, less than x. Our first critical number is 2. Then we're going to have x equals 2. All right, I'm looking at the critical numbers up there. Then we're going to go from 2 to 3 because 3 is a vertical asymptote. Then we're going to go from 3 to 4 because 4 is another critical number. And then we're going to see what happens at 4. And then we're going to go from 4 to infinity. So we're going to have f of x, f prime of x, f double prime of x. How you like my straight lines? And conclusion. So let's take a look at our two derivatives. Our first derivative is x minus 2 times x minus 4 over x minus 3 squared, which again, the bottom is always positive unless it's 0, which happens at the asymptote. So we're not going to worry about that. Otherwise, it's always positive. F double prime of x has a constant in the numerator, which is always positive. And so all we care about is the sign in the denominator. So that's kind of nice. So if we plug in for our first region over here, let's just plug in 0, right? 0 is between negative infinity and 2. So our first derivative, when we plug in 0, our bottom is always positive. The top, when I plug in 0 here and 0 here, I'm going to have a negative times negative. So that's a positive in the numerator. I'm going to get a positive over a positive. So this is a plus sign. Plugging in 2 to our function, right? F of 2 is equal to 2 squared minus 8 over 2 minus 3. That's going to give us a negative 1 in the bottom and a negative 4 on top. So that's going to be a 4 there. Plugging in 2 into the derivative is going to give us 0 because it's a critical number. I guess we should finish. Let's go back to f double prime and plug in 0 here. If we plug in 0 here, we're going to get a negative 3 cubed, which is negative 27. So f double prime is negative. If we plug in 2 here, we also get negative 1 cubed, which is negative. So that's also negative. Now we're going to plug in for this region here 2.5. Imagine plugging in 2.5 here and 2.5 there. That's going to turn this into a positive, right? This first factor will be a positive 0.5, and this one will be a negative 1.5. So the top will be negative divided by positive. So that's going to be a negative here. And plugging in 2.5 here will give us a negative still in the denominator like that. Here we are undefined. And that's where we have a vertical asymptote, right? Now we're going to plug in 3.5 for our next region. And I think we get a positive here and a negative here. And it's positive in the bottom, so we get a negative over a positive, which is negative. We plug in 3.5 over here, we're going to have a positive over a positive, so that's a plus. Same thing if we plug in 4 and anything bigger than 4, right? As long as we're bigger than 3 here, we're going to get positives for our second derivative. And the same idea is going to happen here. If we plug in 4 into our original function, f of 4, it's going to be 4 squared minus 8 over 4 minus 3. That gives us a 1 in the bottom and 8 on top. So that is an 8. Plugging in 4 into the first derivative gives us a 0. And then plugging in something bigger than 4 gives us a positive over a positive. Okay. So now if we come in and write all our conclusions, positive first derivative means increasing. Here we're decreasing. Here we're decreasing. Here we are increasing because of this positive here. Here we are concave down. Here we are concave down. Here we are concave up. Here we're concave up.
Professor?
Yeah, please.
Can you quickly explain the increasing, decreasing, and the concave? Like, how do you get that from what you have?
All right, so see this purple plus sign here?
Yeah.
That means if we have a first derivative that is positive, that means that we are increasing. Positive slopes of tangent lines means the graph is going up.
Okay.
Negative slopes of tangent lines means that it is going down. Cool?
Yeah.
So that's the purple. Now, in green, when we have a negative second derivative, that means concave down. And when we have a positive second derivative, that means concave up. Does it help when I color code it like this?
Yeah, that worked.
Okay, cool. Now, I want to know what's happening at our 2 points, our 2 critical points, right? And so if you look at this region here, purple, we can use, this is the first derivative test. We're going from increasing, right? Positive purple first derivative to 0 slope to negative. That means that we have what happening at x equals 2?
A local max.
Local max. That's by the first derivative test. And if we look over here, we have negative slopes followed by 0 tangent line followed by increasing, meaning we have a local
Minimum.
min. Okay. And so now we're going to start looking at our graph. I'm going to start off with the asymptotes. We had a vertical asymptote at x equals 3. And then we had our oblique asymptote at y equals x plus 3. That's a y-intercept of 3 and a slope of 1. Which looks something like this.
Wait, what was our slant asymptote?
It's right there.
And can you said to explain, asked to explain, I don't get why, because when you did the long division, I forgot why that plus 1 over x minus 3 isn't a part of it.
Okay, let's finish the graph first and then I'll come back to that, okay?
Yeah.
All right. So now let's plot the points that we know. So we had x-intercepts at plus or minus 2.83, 0. So negative 2.83 is about here. And 2.830 is there-ish. And we had a y-intercept at, what was it, 2.67 if I remember correctly. 2.67 is maybe about there-ish. And then we have 2 more points. We have our local max at 2.4. That's right there. And we have our local min at 4.8, which is right there. And so we have those 5 dots, and that's going to help us get there. So if we look at our first region here, it says we are increasing and concave down from negative infinity all the way to 2.
Professor,
So, yeah.
well, where did you get the local max and local mins points from?
So using the first derivative test, we have a horizontal tangent line here and here. You see the 0 for the first derivative?
Yeah.
So horizontal tangent line, and the first derivative test says if we're increasing into that horizontal tangent line and then decreasing out of it, see how I circled in yellow? Increasing followed by horizontal tangent line followed by decreasing is going to have a maximum. Yeah?
Yeah.
And then the pink highlighted, I don't know what shape that is, oval-ish thing, we are decreasing into a horizontal tangent line and then increasing. And so that's how we're getting a local min. That's called the first derivative test.
Yeah, I mean, how did you get the points on the graph?
Oh, well, I took x equals 2 and I plugged it into the original function. And x equals 4 and plugged it into the original function.
Oh, okay, got it.
Cool?
Yeah.
All right. So if we look at our first region from -2 to infinity, we're increasing and concave down. And so that's going to look something like this. Increasing and concave down, going into the local maximum. And then over here, we're decreasing and concave down, and that looks like this. So there is the graph on the left-hand side of our asymptote. And then over here, we're decreasing and concave up, followed by increasing and concave up. and that's going to look like this. Decreasing concave up, increasing concave up. And so that is that graph. Just to make us feel really good about what we've done, here it is on GeoGebra. You can see our asymptotes there, okay? I think I want to do Karash's question last. It's a very good question, but I want to make sure everything else has been answered first, just because it gets a little technical, but I want to hold off on it for just a moment. Any other questions that you guys want to ask about?
Can you just briefly explain the horizontal asymptote again?
You mean the slant asymptote?
No, the horizontal asymptote.
Why there is none?
Yeah.
So the way we find a horizontal asymptote is we take a limit as x goes to infinity. And so in a pre-calc class, often students just memorize if the degree on top is bigger than the degree on the bottom, then there's no horizontal asymptote. That's usually how it's memorized. The way we talked about it is we come over here and we multiply top and bottom by 1 over x in this case, because it's the highest degree variable in the denominator. And when we do that, we get what you see here. And so for huge X, 8 over huge is approaching 0, as is 3 over huge. So when we take this limit, so for huge X, these guys are both going to 0. And so now you just have X, you just have the limit as X approaches infinity of X. Well, as X gets huge, and that's why it's going to infinity. Another way to do it is just to start plugging in numbers, especially if you have a calculator. You would see that, actually, you know what? Let's dovetail this with what Karash is asking. So watch, our original function, f of x is equal to x squared minus 8 over x minus 3. And when we did our long division, we got this equaling to x plus 3 plus 1 over x minus 3. Now, doing long division doesn't change the function. It's just another way of writing it, right? If you put a 1 underneath this, make common denominators, and then combine, you're going to get the same result. You're going to get back to here. Okay, so these are the same thing. The thing to notice when we rewrite this function as x plus 3 plus 1 over x minus 3. As a matter of fact, just to kind of nail that home even further, let me put that in right here. Watch. If I come over here and I put in a new function, g of x is equal to x plus 3 plus 1 over x minus 3, it is exactly the same function that we have in green, right? There's our green function. It's a little much. And here is our black function, right? Here, let's make black purple. So there's our purple function. There's our green function. They're identical. So they're the exact same function, okay? Now, what happens when we talk about huge X, okay? In other words, imagine if I put f of 10, f of 100, f of 1000. This is going to be 10 plus 3 plus 1 over 10 minus 3. That's going to be 13 plus 1 over 7. This one's going to be 100 plus 3 plus 1 over 100 minus 3. That's going to be 103 plus 1 over 97. And then here we have 1,000 plus 3 plus 1 over 1,000 minus 3. That's going to be 1,003 plus 1 over 997. And so, Karash, if you look at this, what do you notice is happening with these fractions here? Don't worry about the first part yet. We'll
They're
talk
getting
about that.
closer to 0.
They're getting closer and closer to 0, meaning they're becoming less and less consequential the further we go, right?
Yeah.
As Hansel put it earlier, he said it becomes very negligible, meaning very close to 0, okay? And so what that is the yellow part is the vertical difference between the slant asymptote and the graph. Let me show you what I mean. If I come back to our graph here and I bring back our asymptote, and we make it dotted again, okay? There is a vertical distance here that is relatively large, but as we go further in this direction, it's becoming smaller, right? And that's that little fractional part we're talking about. The further out we go to the right, the vertical difference between the curve and the line becomes smaller and smaller. That vertical difference is demonstrated by this fractional part right here. Do you see what I'm saying, Parash?
Yeah.
And so we talk about, okay, well, for huge x, this part goes to 0, and the function g of x, which is our purple function, is getting really close to just this line, y equals x plus 3, because this part is getting close to 0. It's becoming negligible. It's becoming
Yeah.
incredibly small.
Okay.